So let's try to see the vocabulary. Again, what are the words that this model was trained on? So we're going to ask for the first model and the tokenizer to give us all the vocabulary that it has, all the items. So we can see that we have 30,522 tokens. And if we randomly check 20 of those, we can see some words, some numbers, some controls, and some suffix, and so on. So this is a small selection of the tokens that we have in the vocabulary. Again, it's quite big, 30,000 tokens and more. Let's focus on our interest. Here we are sorting the items and we are looking for the word interest, finding its index, and then printing out the words around it. So the 3037 is interest, but the 3036 is security, 3035 is queen, and so on. So we can see the environment of this word. There are many tokens here, but we can see more or less what kind of tokens do we have here, especially if we are focusing on the word interest. Now let's move to the embedding transformer model. After we saw the first step of the tokenization, now we want to see what the model does with those tokens. So we can check that the model has a few steps. One of them is the transformer, the one that we're going to dive deeper in a second, but also some other steps like pooling and normalization that are used a lot in deep learning. Each model will have different architecture. This is what they selected for this model. But I want to focus on the transformer. This is the interesting part. I load the transformer by accessing the first model. And if we print it, we can see that the first phase is the embeddings. We're going to now dive into the embedding part. Later on, we can see that the encoder will use the self-attention to translate the words or the tokens embedding into a sentence embedding. Okay, so let's focus on the embedding. We can see that we have multiple parts in it. One is the word embedding, which is taking the large vocabulary, the 30,522, and the size of each embedding is the 384. This is the dimension of the vector that we're going to embed each one of the words. Then we have the position embedding. It is a word on the first, in the sentence, the second sentence, third sentence, and so on, will have different meanings. So this is the position encoding. You can see that we can have up to 512 tokens. So if we feed larger chunk, it will just ignore it. Therefore, we want to have our chunks smaller. Again, 512 tokens is quite a lot, but it's still limited. And we have a few types of tokens. We're going to see them later on, the control, the suffix, and the whole words. There are also some technical layers like the layer normalization and dropout that this architecture defined. If we check the embedding model, the input tokens. So what it means is that we take the first sentence, we tokenize it, and then we check the input ID of each one of those embeddings of the first sentence and the second sentence. And we can see that we have this tensor, and let's understand what does it mean, those numbers. We have this kind of a table built from reading the first element, the second element, and the third element of the shape. The embedding is that we have the text. The text has the bit size, so we can have multiple sentences. Here we have one sentence. This is why the bit size is 1. Number of tokens. So the input of this I have no interest in politics is 8 tokens, as we saw before. Second one is 9 tokens, and the embedding dimension is 384. So each one of the tokens is encoded in a vector the size of 384. So this is our input. If you want to continue and compare those inputs, this table shows the first sentence, start, I have no interest in politics, and the second one, start, the bank's interest rate rises. You can see that the control token at the beginning and the control token at the end are exactly the same. And also the word interest. In both inputs, the word interest is encoded with exactly the same vector. So far, we didn't apply any context. We didn't use the transformer. We only did a lookup to the word embedding of the tokens. We don't have the context yet. So remember this number, the one, which is the input token similarity. We can see some other similarities, but they're quite small. And this is the one that we care about because it's the same word. We can load the whole vocabulary. Consider that we have a matrix of 30,522. all the tokens, and 384, each token vector. And we're going to use a process called TSNE that does two-dimension projection of a very large dimension. So here we are projecting from the 384 into 2, so we can visualize it nicely. It will take a while based on the speed of your machine. I will skip quickly to the end of it. So it took me almost 2 minutes to calculate that, but now I got the metrics of 30,522, but only 2. This is the two-dimension projection, and we can take this and create some kind of a nice visualization. First, we will color each one of the tokens differently. So the control tokens will be in red. The suffix token, the one that start with those pounds, will be in blue. And the words, the whole words will be in green. This is the legend. And then let's create a visualization. So I'm using Altair here, so we can zoom in and zoom out and see the different tokens. We can see that here on top we have a bunch of red ones, so all the control are quite similar to one another. We don't care too much about them. Let's see this area here. We can see here that we have numbers, but those numbers are special. Those are 4 digits number, and they represent years probably. So this is why they are quite similar to one another. They are together. We have this strange token, which is not a year, it's Cromwell, and it's close to 1612 and so on. These are the years that Oliver Cromwell was active, but this is why he probably found itself closer to those years. We can zoom in on different areas and find some word similarity. So here we have violins and harp and other and cello and so on. So musical instruments are somewhat together, and the same will be to other clusters of words together. You are most welcome to explore, choose an area and see if you can understand why those words are together. Most times it will be very easy to understand because of their semantic, which comes from the document's input. Okay, so now we understand more or less what is the input. It is each word was translated to a vector, and similar words are close together.